ট্রাই করবো যে সাইকেল স্টার্ট হইতে কোনে complex 4 or proteins. Electron AD. Is then oxidized with a transfer of electron to cytochrome C where cytochrome B C complex. Complex tray. Cytochrome C is a small protein attached to the outer surface of the inner membrane and is a mobile carrier for transfer of electron between complex 3 and 4. Complex 4 referred to as cytochrome C oxidase complex containing cytochrome A and A3 and 2 copper center and 2 copper center. When the electron passes from one carrier to another by complex 1 to 4 in the electron transport from 1 to 4, they are coupled to ATP synthesis complex 5 for the production of ATP. For the production of ATP from ADP and inorganic phosphate the number of ATP molecules synthesized depend on the nature of electron donor oxidation of one molecule of ADP gives rise to 3 molecules of ATP. One molecule of ADP is given rise to 3 molecules of ATP. While the rate of one molecule of FADH2 produce 2 molecules of ATP. Although the aerobic process of respiration takes place only in the presence of oxygen, the role of oxygen is limited to the thermal stage of the process. Yet, the presence of oxygen is vital since it drives the whole process by removal of hydrogen from the photophosphoration when it is light energy it is utilized from the energy of oxidation reduction and transportation process. It is in respiration for this reason that the process is called oxidative phosphorylation. You have already studied about the mechanism of membrane-leaf ATP synthesis as explained by chemoosmotic hypothesis in the earlier chapter. As mentioned earlier, the energy released during the electron transfer system is utilized in synthesis of ATP with the help of ATP synthase complex 5. This complex consists of 2 major components, F1 and F0. This complex consists of 2 major components, F1 and F0. The F1 headpiece is peripheral membrane protein complex and contains the site for synthesis of ATP from ADP and contains the site for synthesis of ATP from ADP and inorganic phosphate and inorganic phosphate F node is an integral membrane protein complex that form the channel through which proton across the inner membrane. The passage of protein through the channel is coupled to the catalytic side of the F1 component for the productions of ATP. For the productions of ATP, for each ATP produce 4 hydrogen and pass through F node from the intermembrane space of the matrix. Intermembrane space, intermembrane space of the matrix. Down the electrochemical proton, down the electrochemical proton gradient, down the electrochemical proton gradient. Dichromatic representation of ATP synthesis in mitochondria. Outer side, outer side 4 hydrogen F1. Inner side, that is head piece, inner side head piece. ATP ATP reduced into ADP and phosphate reduced to ATP. Matrix ATP, ADP, phosphate are in matrix. F node is present in intermembrane space and outer side 4 hydrogen, that is intermitochondrial membrane. 4 hydrogen intermitochondrial membrane. The respiratory balance. It is possible to make calculations of the net gain of ATP for energy for every glucose molecule oxidized, but in reality this can remain only a theoretical exercise. This calculation can be made only on certain assumptions that there is a sequential orderly pathway functioning with one substrate forming the next, and with glycolysis as a cycle, electron transport system following one after another. The NADS synthesized cytoplasm in glycolysis is transferred into the mitochondria and undergo oxidative phosphorylation. NADS synthesized in glycolysis is transferred into the mitochondria and undergo oxidative phosphorylation None of the intermediate in the pathway are utilized to synthesize any other compound. None of the intermediate in the pathway are utilized to synthesize any other compound. Only glucose is being respired. No other alternative substances are entering the pathway at any of the intermediate stage. Only glucose is being respired. No other alternative substances are entering in the pathway at any of the intermediate stage. But these kind of assumptions are not valid in a living system. All reason But these kind of assumptions are not really valid in the living system. All pathways work simultaneously and do not take place one after another. Substrate enter the pathway and are withdrawn from it as and when necessary. ATP is utilized as and when needed. Enzymatic rates are controlled by multiple means, yet it is useful to do this exercise to appreciate the beauty and efficiency of the living system in expression and storing energy. Hence, there can be net gain of 38 ATP molecules during aerobic respirations of one molecule of glucose. A net gain of 38 ATP molecule during aerobic respiration. Now let us compare fermentation. Net gain of only 2 ATP. Fermentation 2 ATP and aerobic respiration 3 ATP. Net gain of ATP in fermentation is 2 ATP. In anaerobic fermentation 2 ATP and aerobic respiration 3 ATP. Fermentation and account for only a partial breakdown of glucose, where in aerobic respiration it is completely degraded to CO2. CO2 in Krebs cycle. and H2O. In fermentation, there is a net gain of only 2 molecules of ATP for each molecule of glucose degraded to pyruvic acid, whereas many more molecules of ATP are generated under aerobic respiration. Aerobic respiration degraded to pyruvic acid, where many more molecules of ATP are generated under aerobic condition. NADH is oxidized to NAD plus and later slowly in fermentation. However, the reaction is very vigorous in case of aerobic respiration. Vigorous reaction is very vigorous. Very vigorous NADH, NAD plus. Amphibolic pathway anabolism plus catabolism. Amphibolic pathway is glucose is the favorite substrate. Glucose is the favorite substrate for respiration. All carbohydrates are usually first converted into glucose before they are used for respiration. Other substrates can be respired as has been mentioned earlier, but then they do not enter the respiratory pathway at the first step. To see the point of entry of different substrates in the respiratory pathway, fat would need to be broken down into glycerol and fatty acid first. If fatty acid were to be respired, then would first be degraded to acetyl coenzyme and enter the pathway. Glycerol would enter the pathway after being converted to PGAL. The protein would be degraded by protease and the individual amino acid after deamination, depending on their structure, would enter the pathway at some stage within the Krebs cycle or even as pyruvate or acetylcholine A. Since respiration involves breakdown of substrate, the respiratory process has traditionally been considered a catabolic process, and the respiratory pathway is a catabolic pathway. But in this understanding, correct, we have discussed above at which point in the respiratory pathway different substrates would enter if they were to be respired and used to derive energy. Fatty acid would be broken down to acetyl coenzyme A before entering the respiratory pathway when it is used as a substrate. But when the organism needs to synthesize fatty acid, acetyl coenzyme would be withdrawn from the respiratory pathway for it. The respiratory pathway comes into the picture both during breakdown and synthesis of fatty acid. Similarly, during breakdown. Similar during breakdown of synthesis of protein to respiratory intermediate from the limb. Breaking down process within the living organism is catabolism and synthesis is anabolism. Because the respiratory pathway is involved in both anabolism and catabolism, it would hence be better to consider the respiratory pathway as amphibolic pathway rather than as catabolic one. Interrelationship among metabolic pathways showing respiration mediated breakdown of different organic molecules CO2 and H2O, ATP, fats and protein, carbohydrates, Fats, carbohydrate, fats, carbohydrate, protein, fats broken to fatty acid and glycerol, carbohydrates, simple sugar, glucose, protein, amino acid, glucose 6 phosphate, fructose 1 6 bisphosphate, dihydroxyacetone phosphate and glycerol 3 phosphate, pyruvic acid, acetyl coenzyme A, Krebs cycle, O, acetyl coenzyme H2 and CO2 are released. A respiratory quotient. Let us now look at another aspect of respirations. As you know, during aerobic respirations, O2 is consumed and CO2 is released. The ratio of the volume of CO2 equal to the volume of O2 consumed in respiration is called respiratory quotient or respiratory ratio. Respiratory quotient equal to volume of CO2 equal by volume of O2 consumed. The respiratory quotient depends upon the type of respiratory support used during respiration. When carbohydrates are used as substrate and are completely oxidized, the respiratory quotient will be 1 because equal amount of CO2 and O2 evolve and consume respectively. Glucose N6 CO2 H2 plus energy. Respiratory quotient equal to 6 CO2 plus 6 O2 equal to 1.0 carbohydrate. When less than 7 fats are used in respiration, the respiratory quotient is less than 1. Calculations for a fatty acid tripalmethane if used as substrate is shown. 145 CO2, 145 CO2, 102 CO2 plus 98 H2O plus energy. Respiratory quotient equal to 102 CO2 plus 145 O2 equal to 0.7. What is important to recognize is that in living organisms, respiratory substrates are often more than one. Pure protein or fats are never used as respiratory substrate. Plants, unlike animals, have no special system for breathing or gas exchange. Stomata and lenticles allow gases exchange by diffusion. Almost all living cells in plants have their surface exposed to air. The breaking of carbon-carbon bonds of complex organic molecules by oxidation cell leading to the release of lots of energy is called cellular respiration. Glucose is the favorite substrate for respiration. Fats and protein can also be broken down to yield energy. The initial stage of cellular respiration takes place in the cytoplasm. Each glucose molecule is broken through a series of enzyme catalyst reaction into two molecules of pyruvic acid. This process is called glycolysis. The fate of the pyruvic depends on the ability of oxygen in the organism. Under anaerobic conditions, either lactic acid fermentation or alcohol fermentations occur. Fermentation takes place under anaerobic conditions in many prokaryotes, unicellular eukaryotes, and in germinating seed. In eukaryotic organisms, aerobic respiration occurs in the presence of oxygen. Pyruvic acid is transported into the mitochondria where it is converted into acetyl coenzyme A with the release of CO2. Acetyl coenzyme A then enters the tricarboxylic acid pathway of Krebs cycle operating in the matrix of the mitochondria. NADH plus and FADH2 are generated in the Krebs cycle. The energy in this molecule as well as that in the NADH plus synthesized during glycolysis are used to synthesize ATP. This is accomplished through system of electron carriers called electron transport system located on the inner membrane of mitochondria. Electron as they move through the system release enough energy that are trapped to synthesize ATP. This is called oxidative phosphorylation. In this process, O2 is the ultimate acceptor of electron and it gets reduced to water. The respiratory pathway is an amphibolic pathway as it involves both anabolism and catabolism. The respiratory quotient depends upon the type of respiratory support used during respiration.